Swayam Prabha. Digital India. Educated India.
Alright, so last time we introduced the concept of distinguishability and indistinguishability, right. So the background to it was that so when we use the canonical partition function for an ideal gas, and we saw that the entropy is not really defined as temperature goes to 0. The Helmholtz free energy wasn't really an extensive quantity as it should be. And we saw that there is some fundamental problem in the counting, right, and then we realized that it might be because at very small scales it might be possible that the particles are not really distinguishable, in the sense we can't really track their phase space trajectories with confidence. And the fundamental concept underpinning that statement is the quantum mechanics, right, because in quantum mechanics the particles are not really point particles, but they are fuzzy particles, because we can't really measure the position and momentum with complete accuracy, right. And we saw that it might be possible when two particles are interacting with each other. For example, they are colliding with each other, during the collision their wave functions might overlap significantly, in which case we will not really be 100% sure what is the final trajectory of the particular particle, right. So there are possible likelihoods after every event, and after multiple such collisions we we basically lose track of all the particles, right. Say we start with certain tags on all the 10⁻23 particles, but since they are undergoing trillions upon trillions collisions per second, very quickly we will lose track of them, right, in which case we cannot really say that these particles are distinguishable, right. And based upon that and using that concept, we said that so in classical limit, when the particles are much bigger than the de Broglie wavelength of that particular particle, in that case their wave functions during the collision will not really overlap significantly, in which case they will remain distinguishable. However, if the particles are much smaller than their de Broglie wavelength, which is true for quantum particles like electrons, photons and so on, in which case we will not be able to distinguish them, right. So they become indistinguishable, and the exercise that we have started since the last class is basically we are trying to address how the fundamental problem of counting these particles changes as a consequence of them being distinguishable and indistinguishable, right. And essentially in the last class we started with what we called the distinguishable and classical case, which we called Maxwell-Boltzmann, right, Maxwell-Boltzmann statistics. And the way we basically formulated the problem was as follows. So we had a system which was completely insulated from the surroundings, so that its total energy and total number of particles, they do not change with time. And we basically divided the total energy of the system into subgroups starting from epsilon 1. Okay, so we basically divided energy into groups which are epsilon 1, epsilon 2, so on up to epsilon capital G. So into G subgroups, and every subgroup has n1, n2, so on up to ng number of particles, and these energy levels are further split into degenerate energy levels G1, G2 and so on up to Gg, right. And the problem that we are interested in is in this distinguishable classical case, what is the occupancy, right? So, Ni divided by Gi, right. So, number of particles per number of cells in the same energy level, and for Maxwell-Boltzmann we saw that this ratio was given by e raised to power alpha plus beta epsilon I, where alpha and beta are still unknown constants which we have not evaluated yet, which we will do as we progress, and this is basically Maxwell-Boltzmann statistics, right. Okay, and this is for distinguishable particles. Okay, so that is the result that we obtained in the last class, right. But now what we can do is we can move on to the quantum case, right. So, in classical case the particle size is much bigger than the de Broglie wavelength, but however in quantum case the wavelength is much longer than the particle dimension. So, they become indistinguishable, right. So, the next thing that we will do in today's class is quantum statistics. Okay. And like I just said, and this is followed by what is known as quantum particles, which as a virtue of being very tiny, much smaller than their de Broglie wavelength, they are indistinguishable. Okay. And we can typically divide quantum particles into two categories. So, the one is what is known as spin half or spin n by 2 particles, where n is an integer number, and the other one is spin n, right, where n is an integer number. So, spin okay, so let me spin 1 or n, right, spin 1 or n, so where n is an integer number. All right. And typical examples of such particles and these spin half particles, they are also known as fermions, okay. And typical examples are electron, neutron, proton, helium 3 and so on, okay. So, all these particles have half a spin or integer multiple of half spin half, and they are all known as fermions. And one very important property of these particles is that they follow what is known as Pauli's exclusion principle, right. So, remember so far what we had been doing, we are drawing these energy levels epsilon I and splitting them into Gi number of cells and trying to occupy Ni number of particles in these Gi number of cells, right. So, let's draw that schematic now in like 1D schematic, right. Say we have this Gi number of cells, right, Gi cells, and say we have Ni particles, right, and due to Pauli's exclusion principle, which basically states that no two particles can occupy the same cell, right. So, no two particles with all the quantum numbers same, they do not really occupy the same cell, which in our exercise will basically mean that a situation where two particles or more than two particles are existing in the same cell is forbidden, right. So, at maximum we can only put one particle in each cell, all right, and so on, okay. So, there is just one particle or there is no particle in any cell. So, we can't really occupy more than one particle in the single cell, all right, which naturally means, okay, which naturally implies that within a given energy level, the number of particles has to be smaller than or equal to the number of cells, right. So, if there are more number of particles trying to occupy the number of cells which is less than the number of particles, that is not possible, and the particle will jump to maybe higher energy level or so on, okay. And the statistics followed by such particles, which we will derive very soon, is known as Fermi-Dirac statistics. So, Fermi-Dirac statistics. Okay. On the other hand, if we have spin 1 or integer multiple of spin 1, these are known as bosons. Okay, bosons, and the typical examples are photons, phonons. So, phonons are the vibrational modes in a solid, and also like helium 4 and so on. Okay. So, all these particles they have either spin 1 or integer multiple of 1, all right. And again, like the important property is that they do not obey. So, they do not obey Pauli's exclusion principle. Okay, which in this schematic will mean that multiple occupancy of particles within the same cell is actually allowed. Okay. So, you can fit as many particles as you want within a single cell, all right. So, which implies multiple occupancy is allowed. And the statistics followed by these particles is known as Bose-Einstein statistics. Okay. And this is what we will basically do in today's class, right. So, we will derive the expressions for Fermi-Dirac and Bose-Einstein statistics, all right. Okay. So, let us start with Fermi-Dirac. Okay. So, now remember the particles are now indistinguishable, right. So, we cannot really distinguish these particles as they move in the phase space trajectory, as they move in the phase space, right. So, again I will draw this schematic. So, we have this box of these particles which is n in number, and we divide the energy. Okay. So, basically n total particles. So, n indistinguishable particles with E, which is the total energy, right, and we divide this energy into various subgroups epsilon 1, epsilon 2, so on up to epsilon g, right. And every subgroup has n1, n2, so on up to ng number of particles, and these energy groups are further divided into g1, g2, so on up to gg number of cells, right. And in the energy state this looks like this, right. So, again this is like say typical ith cell with energy epsilon I, number of particles ni, and number of degenerate cells which is gi, right, and this is they are all like all insulated, right. So, total energy and total number of particles does not change, all right. And our aim, like in the Maxwell-Boltzmann statistics, we basically counted the number of ways in which we can distribute these particles, right. So, our aim is the same. We are going to count the omega fd, which is total number of ways to distribute n particles in energy, n particles with total energy E, all right. So, that is our aim, all right. And again we are going to evaluate a very similar quantity that we evaluated for Maxwell-Boltzmann, which is basically the Ni divided by Gi, right. So, the number of particles in a given energy state with degeneracy Gi, all right. So, that is the quantity which we are interested in, right. So, now since the particles are indistinguishable, the only thing that we have to do is we just have to find the number of ways in which we can distribute Ni particles in Gi number of cells, right. So, since particles are indistinguishable, we do not, it does not really matter how we divide those distinguishable particles between various energy levels epsilon 1, epsilon 2 and so on, as we did for Maxwell-Boltzmann. So, there we did it because the particles were indistinguishable, but here the particles were distinguishable, but here since they are indistinguishable, our problem basically gets simplified and we just have to concentrate on single energy cell. All right. So, let us say how do we do it. Okay. But before that I would quickly want to remind you that these particles, since they are fermions, right. So, these are fermions. So, they basically obey Pauli's exclusion principle, right. So, due to Pauli's exclusion principle, like I mentioned before, the condition for any given energy level is that the number of particles trying to occupy Gi number of cells has to be less than or equal to the number of cells, right, because like I said, the multiple occupancy is forbidden in this case, right. So, at max we can only put one particle in one cell, we can never put more than one particle in one cell, all right. So, now let us start doing the counting, right. So, what is the number of ways to do that? Okay. So, let us concentrate on ith cell, right. So, we can start the problem in this way. So, we can say that number of ways, say the first particle can be put in the ith cell, in the basically Gith cell, right, and that would be Gi, right. So, say I start with one particle, I can put that particle in any of these cells, right, that is because all the cells are empty. But now once one particle has occupied certain cell, okay, what will be the number of ways for second particle to occupy the remaining Gi minus 1 cells, and that simply will be Gi minus 1, right, because one cell is already occupied and we cannot really put the same particle in the same cell because of Pauli's exclusion principle. And similarly, we can go on, we can go to third cell Gi minus 2, so that will be Gi minus 2 and so on, right. So, if I go to an ith particle, right, so an ith particle, and that number will be Gi minus Ni plus 1. Okay. So, therefore, total number of ways, okay, so total number will be equal to product of all this, right, and this is for the ith energy level, right. So, that will be Gi times Gi minus 1 times Gi minus 2, so on up to Gi minus Ni plus 1, all right. And okay, and another important thing is, now since the particles are indistinguishable, right. So, there is no tag on the particle. So, remember in Maxwell Boltzmann when I gave you an example, so I put the tag 1, 2 and 3 on the particles, but now we cannot really do that because we do not know which particle is which, right. So, therefore, we have to, so the way of doing this is we are over counting it, right, because we are so in this, so this expression tells you that we know which particle is which, right. So, basically since Ni particles that we are trying to occupy are indistinguishable, we have to we are over calculating this and we have to divide by Ni factorial, right. So, the correct, so the right number of, basically the correct value of this will be this total number divided by n factorial, right. So, this will become Gi times Gi minus 1 times Gi minus 2, so on up to Gi minus Ni plus 1 divided by Ni factorial, and you can see that this I can write simply as Gi factorial divided by Ni factorial times Gi minus Ni factorial, right, because all the higher order terms here they will get cancelled here, all right, and this simply becomes GIC Ni, and let us call this the number of ways in which we can distribute Ni number of particles in Gi number of cells in the ith cell, all right, okay, in the ith energy group, all right. So, now what will be the total number of ways in all the G groups, right. So, for all G groups, so that number which we can now call is omega Fd, that will be P1 times P2 times so on up to Pg, right, and this is the product I going from 1 to G Pi, where individual Pi looks like this, right, and I can just write it as follows. So, this is pi I going from 1 to G Gi factorial divided by Gi minus Ni factorial Ni factorial. Okay. And again, like we did the Maxwell-Boltzmann statistics, our next step is now to maximize this, right. So, basically maximize log of this quantity, right, because these are astronomically large numbers. So, it is always convenient to work with logarithms. Okay. So, basically let us take the log. So, log of omega f d simply becomes, so this pi reduces to summation. So, this is I going to from 1 to G, this is log of G I minus log of G I minus N I minus log of factorial minus log of N I factorial. Okay. And again we will use the Stirling approximation. So, which tells us that for any very large number x, so log of x factorial equals x log x minus x, okay, for x very large. All right. So, if we now use this formula and go back to this expression, so we can see log of omega f d basically become sigma I. So, G I log G I minus G I minus G I minus N I log G I minus N I plus G I minus N I, okay, so this is G minus N log N plus N, okay, and you can see few terms they cancel out. So, this G I they go away, sorry. So, this G I goes with this G I and we are left with G I log G I minus G I minus N I log G I minus N I minus this should be I, okay, there is I index here also, okay, and we are left with this. All right. So, which basically becomes log of omega f d equals summation I G I log G I minus G I minus N I log G I minus N I minus N I log N I. Okay. And again for equilibrium to be to establish, this quantity has to maximize, right, and we have to maximize it with, okay, so these are all G. So, we have to maximize this with respect to N I because that is the variable in the problem, right. So, basically maximizing with respect to N I. So, we have delta of this quantity log omega f d. So, we will just take derivative since it has no N I, right. So, this directly gives us 0. So, this becomes, so first we will take derivative of the first term. So, this is so minus minus becomes plus. So, we have delta N I log of G I minus N I minus G I minus N I divided by G I minus N I times the derivative of this thing, right. So, minus delta N I times G I minus N I divided by G I minus N I minus log N I delta N I, sorry, log N I minus N I by N I delta N I. Okay. So, this is what we get, and you can see that there are few terms which straight away cancel out. So, this is basically plus 1 and this is minus 1. So, they get cancelled out, and we have a delta N I here as well. Okay. So, we have a delta N I here as well, and this I can rewrite as, let me take negative sign outside, sigma I log of, so if I take minus sign, this becomes plus, so this becomes Ni divided by this becomes minus Gi minus Ni times delta Ni, and this is equal to 0. Okay. And let us call this equation number 1. Okay. And this is the equation that we want to solve. Okay. But also we know that there are two constraint equations. So, similar to what we were doing in the Maxwell-Boltzmann. Okay. So, there are constraint equations. And that comes from the conservation rule, right. So, we know that total number of particles in the system is conserved, which implies sigma I delta Ni is 0, and this is say our first constraint equation, and also the other condition that the total energy of the system remains constant. Okay. So, this implies sigma I Ni delta implies epsilon I delta Ni is 0, and this is the third constraint equation, right. And we have to solve the equation 1 in the presence of these two constraint equations. Okay. And again the method is the using method of Lagrange multiplier. So, we basically use the trick, which is equation number 1 plus alpha times equation number 2 plus beta times equation number 3 is 0, where alpha and beta are unknown Lagrange multipliers. Okay. And if we do that, our equation basically becomes log of Ni by Gi minus Ni. Okay. So, basically this first equation I have just get rid of the negative sign, plus alpha plus beta epsilon I is equal to 0, this time delta Ni is equal to 0, and since delta Ni is an arbitrary number, it can be 0 and non-zero. So, for this equation to be true, this term inside the parenthesis has to be 0, right. So, this becomes log of Ni by Gi minus Ni equals minus alpha minus of alpha plus beta epsilon I, or I can write this as follows. So, this is Gi minus Ni by Ni equals e raised to the power alpha plus beta epsilon I, or I can write here Gi by Ni is basically e raised to the power alpha plus beta epsilon I plus 1, and this simply means I can now get my final result. Ni by Gi becomes 1 divided by e raised to the power alpha plus beta epsilon I plus 1. Okay. And this is called Fermi-Dirac statistics. Okay. So, this result in box. So, this is Fermi-Dirac statistics. Okay. And remember, alpha and beta are still unknowns, right. We haven't evaluated it yet, which we will do, but this result looks very similar to Maxwell-Boltzmann distribution, except we have an extra plus 1 in the denominator, and that was missing in the Maxwell-Boltzmann statistics, and we will see the consequences of this as we progress. All right. Okay. So, now what we can do is we can now jump to what is known as Bose-Einstein statistics. Okay. So, again we have the similar problem. So, we have this system which is insulated, okay, which is insulated, and we have ith cell, ith energy level with energy epsilon I, in which we are trying to occupy Ni number of particles. right, Ni number of particles. But now since these bosons, right, so this is bosons. So this statistics is shown by the particles which have integer spins, and these are bosons. So they do not really obey Pauli's exclusion principle. So we can have many number of particles in a single cell, right. So we can even have cells without particles, but we can have cells with many particles, all right. So which means multiple occupancy is allowed. But remember, they are still indistinguishable, right, still indistinguishable. Okay, so we still can't distinguish them because still they are quantum particles, but they have this special property that they do not really obey Pauli's exclusion principle, all right. So multiple occupancy in various cells is actually not forbidden. Okay. Okay. So how do we do this, right? So essentially again the problem is we have ith energy level with Ni number of particles and Gi number of cells, right, and our problem is to distribute Ni number of particles in Gi number of cells, all right, and Ni particles are indistinguishable. Similarly, Gi cells are also indistinguishable because they belong to the same energy level, all right. So basically the problem is as follows. So Ni particles and Gi cells are separately indistinguishable, right, indistinguishable. Okay. So it is like these cells are indistinguishable among each other, and these number of particles are also indistinguishable among each other, all right. It is like, say, you have blue marbles and red marbles, right. So you can distinguish between blue and red marbles, but you can't distinguish between within the blue marbles, all right. And again, since the problem is basically counting the number of states, because that will what give us the number of microstates, and that is what will maximize. So let us see how we can do it, all right. So let us try to visualize it. So we have these Ni number of particles, which are these tiny circles, and we have these Gi number of cells, which are these tiny squares. And the problem basically reduces to how can we distribute these particles among each other, right. And you can see that if we have two species of particles with numbers Ni and Gi, so the number of ways in which we can distribute that is basically given by this. So number of ways is basically the total number of particles factorial divided by the number of individual particles which are alike, right. So Ni factorial Gi factorial. Okay. So we can divide by this over counting. Okay. And when we do that, typically the typical configuration looks like this, right. So when we mix these particles, two species of these particles together, we typically end up with configuration which can look something like this, right. So we can even have no particle next to no circular particles next to a square box, and we can have few particles, okay, and so on. Okay. So this is how typically they will get distributed. Okay. And the way we can visualize this is as follows. So what we can do is we can say that the number of particles on the left of this box, they are inside this box, right. So this way we can always like visualize. So this has like no number of particles, this also has no number of particles, and so on, okay, something like that. Okay. But the issue is that when we do counting in this way, we also end up with a typical situation which looks something like this, right. So where we have all these particles which are put on the left and all these particles which are put on the right, okay. And when we use this formula, we are also calculating a single instance where all the particles are outside and all the cells are separated, right. So, which means we are counting a situation where there are no particles in any of the cells, but all the particles they are kept outside, right, and that does not really make any physical sense, all right, because we want particles to occupy these cells. So, there is like slight bit of confusion or problem with such a reasoning, and the way to basically solve is to rather than working with GI number of cells, we work with GI minus 1 cells, so that we can always assign. So, what we can do is we can remove one of these GI cells, okay, and put it here, okay, so that one cell is always assigned to these many particles, right. So, basically this is the situation with Ni particles and GI minus 1 cells, so that we can overcome the problem where all the particles were like floating outside the number of cells, all right. So, this is like this tiny conceptual issue with with counting these particles in this manner, all right. But we will see that it does not really matter, because the number of cells that we are talking about is very large number, like much larger than 1. So, we can always ignore this minus 1, all right. So, therefore, anyway let us proceed. So, the true number of ways, okay. So, we argued that the number of ways is Ni plus Gi factorial divided by Ni factorial Gi factorial, but the true number of ways will become Ni plus Gi minus 1 factorial divided by Ni factorial times Gi minus 1 factorial. So, that the situation where all these particles are occupying one cell is always there, all right. So, we do not confuse all the particles occupying one cell with a state where all the particles are outside this energy in the outside of these cells, all right. But again okay. So, that is and let us call this number as Pi, right. So, this is the number of ways to distribute Ni particles in Gi cell in ith energy level, okay. So, then what will be the total number, right. So, total number among all the energy levels, which we can call omega Be, that is basically product of all these Pi's, okay. So, this is Pi. Okay, so, this basically becomes product I going from 1 to G, Ni plus Gi minus 1 factorial divided by Ni factorial times Gi minus 1 factorial, okay. And again since Ni and Gi are much greater than 1, we can write Gi minus 1 as Gi and Ni plus Gi minus 1 as Ni plus Gi. So, therefore, it reduces to this. Again, like we can now take logarithm on both sides, all right, and okay. So, this I can write. So, log of omega Be I can write as, so this becomes sigma summation I, and this basically becomes log of Ni plus Gi factorial minus log Ni factorial minus log Gi factorial, okay. And again we will use the Stirling's approximation and do little bit of algebra. So, this becomes Ni plus Gi log Ni plus Gi minus Ni plus Gi minus Ni log Ni plus Ni minus Gi log Gi plus Gi, all right. And you can see that this cancels with this Gi gets cancelled with this, and we are left with sigma I times Ni plus Gi log of Ni plus Gi minus Ni log Ni minus Gi log Gi. Okay. And again our next step will be to maximize this quantity with respect to Ni and then we write down two constraint equations and we solve it. So, basically the same steps that we followed for Maxwell-Boltzmann and Fermi-Dirac. Okay. So, what will be the delta of log of omega Be, that will become equal to sigma I log of Ni plus Gi plus Ni plus Gi by Ni plus Gi times delta delta Ni. Okay. So, there will be delta Ni here as well, maybe I can write delta Ni is outside. Okay. So, delta Ni minus log of Ni minus 1 delta Ni, and this we have to equate to 0. Okay. And you can see this gets cancelled out, and we are left with negative I log of Ni divided by Ni plus Gi times delta Ni is equal to 0, and again let us call this equation number 1. We also have two constraint equations, right. So, two constraint equations. So, the first one is sigma I delta Ni is 0 and sigma I epsilon I delta Ni is also 0, right. So, this is 2, this is 3, again using the method of Lagrange multiplier. So, we do 1 plus alpha times 2 plus beta times 3 equals 0, and when we do that, so we basically get sigma I log of Ni divided by Ni plus Gi plus alpha plus beta epsilon I and equated to 0 times delta Ni and equated to 0, and again for this equation to be 0, since delta Ni is an arbitrary number, so this has to be 0, right, term in the parenthesis has to be 0, and we can write log of Ni divided by Ni plus Gi equals minus alpha minus beta epsilon I. Okay. And again I can like simplify this. So, this can be written as 1 plus Gi by Ni equals e raised to the power alpha plus beta epsilon I. So, basically I have just taken exponential on both sides and taken inverse of this. Okay. So, I have moved it to the left hand side and moved this to the right hand side, and you can very easily check that in this case the final result is Ni divided by Gi, the quantity that we are interested in, that becomes e raised to the power alpha plus beta epsilon I minus 1. Okay. And this distribution or this statistics is known as Bose-Einstein statistics. Okay. So, this is the Bose-Einstein statistics we are interested in. Okay. So, all right. So, the next thing that we have to do is again we have to evaluate alpha and beta, but maybe I can quickly summarize, right. So far what we have seen is we have derived the quantity Ni by Gi for three cases. One is Maxwell-Boltzmann, which is classical and distinguishable. Okay. Classical distinguishable. The other one is Fermi-Dirac, which is quantum indistinguishable. And the third one is Bose-Einstein, which is again quantum and indistinguishable. Okay. And basically the distribution of particles, which now we can write as FMB, which is again the quantity Ni by Gi. So, this we saw that this was 1 divided by e raised to the power alpha plus beta epsilon I. The quantity for Fermi-Dirac is again Ni by Gi is 1 divided by e raised to the power alpha plus beta epsilon I plus 1. Okay. So, this is, and for Bose-Einstein this is 1 divided by e raised to the power alpha plus beta epsilon I minus 1. Okay. But now here alpha and betas are unknown, right. So, alpha and beta. So, we have to evaluate them, all right. So, let us do that. Okay. So, evaluation of let us alpha and beta. Okay. So, today we will first do beta and then we will do alpha. Okay. So, let us start with the Maxwell-Boltzmann statistics, right. So, we know for Maxwell-Boltzmann statistics Ni is given by Gi times exponential of minus alpha minus beta epsilon I, okay, which implies I can just write my Ni by Gi as e raised to the power minus alpha e raised to the power minus beta epsilon I. Okay. So, and the way we evaluate beta is as follows. So, we use the condition. Okay. So, since total number of particles sum over Ni is n, right, and this implies I can write this as follows. So, I can just move Ni Gi to the right hand side and take summation, and that will be n, right, which implies n will be summation I times Gi e raised to the power minus alpha e raised to the power minus beta epsilon I. Okay. And since alpha has no I index, so this this term has no I index, so this comes out Gi e raised to the power minus beta epsilon I. Okay. Now, let us call, okay, so call this quantity, okay, so call sigma I Gi e raised to the power minus beta epsilon I, let us denote it by Z. Okay. And this might look familiar to you, because if this beta indeed was 1 divided by kBt, okay, this quantity will actually be the partition function, right, the canonical partition function with degeneracy, right, for with every energy level epsilon I with degeneracy Gi. Okay. All right. So, therefore, if we do that, we can write from this equation. So, if this becomes Z, so I can write n divided by Z becomes e raised to the power minus alpha. Okay. And since e raised to the power minus alpha, okay, so the e raised to the power minus alpha is Ni divided by Gi times e raised to the power beta epsilon I from this equation. So, this is Ni divided by Gi times e raised to the power beta epsilon I. Okay. So, which implies I can write my Ni by Gi in another way, which is as follows. So, this is n divided by Z. So, I am taking it to the other side e raised to the power minus beta epsilon I. So, therefore, now we have to basically what we have to do is we have to substitute this into an equation that we actually saw in the last class, right. So, remember when we were deriving the we were maximizing the log of omega of Maxwell-Boltzmann, right, log omega mb in the last class. So, we stumbled upon an equation from the previous class. So, we saw So there was an equation that we ended up with. So log of omega mb is basically given by n log n plus sigma of I times ni log gi minus ni log ni. Okay. So you have to go back to the previous class and you have to check that this equation we indeed wrote this equation, okay, and I can now rewrite this equation in a different manner. So this becomes n log n plus sigma I times ni times log of gi by ni. Okay. So this is gi by ni. Okay. And what we have to now do is we have to substitute. Okay. So I can write here gi by ni basically becomes z by n, I am inverting this equation, times beta epsilon I, right. So I can substitute gi by ni with z by n times e raised power beta epsilon I. Okay. So this I can write log n log n plus sigma I ni log of z by n e raised power beta epsilon I. Okay. And again now we can like simplify it even more. So n log n plus okay, so what okay, so this basically becomes ni times log of z plus beta epsilon I minus log of n. Okay, I am just splitting this log, okay, and this basically becomes n log n plus I sigma I ni log z plus sigma I ni beta epsilon I minus ni minus I ni log n. Okay. And log n I can take out, and sigma the summation ni basically is n. So this term cancels out. Okay. And we are left with the following term. So this is okay. So this basically means, so log of omega mb is basically equal to sum over I ni log z plus, and again beta I can take out, what is sum over ni times epsilon I, that is basically the total energy, right. So this is beta times total energy E. Alright. So what we will do now is we will use the statistical definition of entropy to rewrite this equation in terms of S, right, the entropy variable S. So since S is given by kb log of omega mb, right. So this implies S becomes kb times sigma I ni log z, okay, basically this equation plus beta E. Okay. And I can write my, so I can take it inside. Okay. So this becomes S equals kb, and log z has no I index. So and this sum over ni is basically total number of particles, kb times n times log of z plus kb times beta times E, right. And we know that since our system is isolated, right, and if I take the ensemble average of this energy E over various ensembles, so this basically is equivalent to the internal energy, right. So since the system is isolated, I can write my E to be equivalent to U, which is the internal energy, right, in thermodynamics. So what I can basically rewrite this equation now in terms of U. So S equals kb times n log z plus kb times beta times u. Okay. Um, and now we will use the statement of first law, right. So, first law states that du equals TdS minus PdV, which implies I can write my temperature to be partial derivative of internal energy with respect to entropy at fixed volume, or I can write the inverse temperature as partial derivative of entropy with respect to internal energy at fixed volume. Okay. And let us now take partial derivative of this equation with respect to u, right. So, basically from this equation I can write del S by del u at constant volume, which is indeed 1 by T, and that becomes n kb by z, derivative of z with respect to beta, and then derivative of beta with respect to internal energy u at fixed volume, right, plus beta kb, first derivative of just the u and then the other term. So, kb u times derivative of beta with respect to internal energy at fixed volume. Okay. And let us call this equation number 1. Okay. But remember what is z, okay. But since we defined z to be sigma I gi e raised to the power minus beta epsilon I. So, this implies my del z by del beta is equal to negative of sum over I gi epsilon I e raised to the power minus beta epsilon I, right, and let us call this equation number 2. Okay. So, all I have done is I have just taken its partial derivative with respect to beta. Okay. And I have gotten this term del z by del beta, which eventually will substitute into equation 1, and another and we will use another quantity, another property, right. So, since total energy E, right, which is equivalent to U, like I said before, is basically sum over I n I times epsilon I, right, and to simplify this little bit, we will multiply and divide by this quantity z I n I epsilon I times z, and now I can write the form of z. So, this becomes n I epsilon I gi e raised to the power minus beta epsilon I. Okay. And this essentially becomes so this essentially becomes n divided by z sum over I epsilon I gi e raised to the power minus beta epsilon I. Okay. All right. So, which implies I can write my energy as n by z times and since we saw that the partial del z by del z beta is basically minus sigma I epsilon I e raised by minus beta epsilon I. Okay. So, which is a similar quantity. So, there is a minus sign, and this basically becomes del z by del beta, and this comes from equation 2, right. So, from equation 2. Okay. So, and this is basically equation 3. So, what we will now do is we will substitute equation number 3, result obtained in 3 and 2, and put it into 1. Okay. So, therefore, what we get is 1 by T, right. So, this I am just rewriting this equation again. So, 1 by T equals minus, okay. So, 1 by T is, so I am just substituting here. So, minus of n kb divided by z times zu by n times del beta by del u. Okay. So, del beta by del u at constant volume plus beta kb plus kb times u of del beta by del u. Okay. And this is basically I am substituting for u from here. Okay. All right. So, and we can see that this so this z cancels out, this n cancels out, and this entire term cancels out with this, and eventually we are left with 1 by t equals beta times kb. Okay, and this leads us to our final final result, which means my beta is nothing but 1 divided by kbt. Okay, so this is the Lagrange multiplier number 2, right. So, the beta Lagrange multiplier. Okay. So, in the next class we will also evaluate the other Lagrange multiplier alpha. Okay. So, see you in the next class. Thank you.